And we have a wonderful session, including a joint session with Usable Security. That's a first that we're looking forward to very much. So we'll dive right in to our program. And I believe our first speaker is Bert Hubert from PowerDNS. And I'd like it if the speakers would introduce themselves, it'll be less fuss. So Bert, you can give a little introduction to yourself and dive into your talk. And I'm going to put Zoom back on because you're going to control the talk from there. Am I, he's got it. Okay, good. So here we go.
So, with some luck, you should see my presentation now.
Yes, we see it well.
Okay. Well, good morning, everyone. Can you hear me well?
Yes. Yes.
Okay. Yeah, a brief introduction. I'm Bert Hubert. I'm the founder of PowerDNS. We've been around since 1999 or something like that. And we are an open source company. We write open source name server software and also closed source components, which are used by some of the largest domain name hosters in the world. And also used by some of the largest access providers of the world. And these days, while I will forever be the founder, I am now also sort of managing things, but I'm aching to get back to programming. Okay. With that, I'd like to start my presentation. Can I get one confirmation that people can actually hear me?
Yes. Yes.
Okay, very good. So what I want to talk about today is a thing called Ipcipher, which is an interoperable way to encrypt IP addresses in place. By in place, we mean that if you have tooling that currently processes IPv4 or IPv6 addresses, this allows you to encrypt an IP address to something that is again an IP address, just a different one. And that has benefits for privacy and compliance and other stuff, but still allows you to do the analysis that you need to do. So why are we at this stage? Why is this suddenly happening? In this presentation, I will cover the why you should do this, how you should do it, what does it get you, and how to actually watch out for any pitfalls when you are encrypting IP addresses to make sure that it's even remotely secure. So we're living in a very interesting time. I'm dialing in from Europe. In Europe, we are going privacy crazy. We're currently rolling out the GDPR privacy regulations. And these are sort of scarier than the year 2000, for those of you that remember. That completely changes the privacy landscape, and it will actually turn private data into toxic waste. Several other things are going on at the same time here. We're, of course, still sort of absorbing the Equifax data breach, and we're also facing the rollout of the Network and Information Systems Directive, which comes with such fun stuff as 4% of your revenues fines if it turned out that you've not been paying enough attention to privacy or availability. So it is a hot... of course, we've always cared about privacy, but privacy is now very quickly turning into a monetary matter. Private data, as shown on the left, as a log file with IP addresses, is starting to become toxic waste. And in the sense that if you have the private data, the best way to think of it is as very dangerous goods that must be administered very tightly. And if they leak, you are in a world of pain. But like toxic sludge and toxic waste, it can be processed into less harmful forms, and that's what we're talking about here. But the story here is pseudonymization, and this is defined, this is privacy officer language, as the separation of data from direct identifiers so that linkage to an identity is not possible without additional information that is held separately. So in short, it means replacing full names by user IDs, numbers, or it means changing IP addresses into other IP addresses. And this is no get out of jail free card, although in fact it may end up being an actual get out of jail free card. But it can reduce the risk of privacy leaks. It cannot remove the risks associated with privacy leaks, but it can help you protect data even as you're still able to process it. So what's the goal? The goal of the story is obfuscate customer IP addresses while still allowing your own employees and potentially other companies' employees to analyze your traffic for attack data or latencies or malware or whatever, and continue to do this using our favorite regular tools such as TCP dump and grep and awk and sort and unique, or your huge Hadoop big data processing pipeline that wants to see IP addresses. So this is what it looks like. You take a normal IP address and you apply an operation to it, and it becomes a different IP address that can be transformed back into the original IP address. And what you can see from here is that the one thing that's immediately obvious is that whenever you encrypt an IPv6 address, it becomes a lot longer because all the embedded zeros are no longer zero after encryption. So what's the history of this? In 2006, the PowerDNS recursor was a very, very unproven program. And people were worried about rolling it out because it was a resolver, it was not proven. And our first big deployment was Access for All. And Access for All is was the earliest internet service provider in the Netherlands, and they came straight out of the hacker scene. And they are extremely privacy conscious. So they said, we want to roll out the PowerDNS recursor, and we want to be able to share PCAPs with you of things not going well. But we need to strip all the IP addresses from those PCAP files, and which is a very reasonable request. So in 2006, we made a tool called DNS Washer, and it replaces the first customer IP address it sees by 0.0.0.1, and the second one by 0.0.0.2, which is already sort of nice, and it works. And we've been using that since 2006 continually, and we're sort of amazed that not everyone is using these tools to strip IP addresses from PCAP files. The big issue with this tool is that, let's say you know you are under attack from some of your users, you strip the IP addresses using DNS Washer, and then you finally identify a harmful IP address in the washed PCAP, and then you have the huge task of turning that back into, who actually was that? So you get this IP address 0.0.0.12. What was the original IP address behind that? So this was a one-way encryption street, and there was no real way back. So what we would love to have is that you take these two lines of PCAP and encrypt them, so that those are the top two lines, and then encrypt them to the middle two lines. You perform all your analysis on the encrypted IP addresses, and you find out that 232.226.235.224 is your harmful customer or your malware-infected customer or whatever. You report that back and you say, well, I have done my analysis, I have figured out who the guilty party is, and then finally the people with access to that data are able to decrypt the PCAP again and see, well, I can see this was the harmful or the relevant IP address. So this is a two-way street encryption and decryption in place within existing PCAP files or within existing log files, or actually anything that has IP addresses in there. So it's important at this stage to realize that this kind of encryption, even though we use the big word encryption, even after you have done this kind of encryption, it is not safe to publish that file, to share that file with anyone. Because even IP addresses that have been changed can be re-identified until the original user. It is not good enough to run your PCAP through DNS Washer and then put it on Dropbox and tell the world to analyze it. And if you are looking at Ipcipher through that lens, you will be sorely disappointed, because that's not the security level that we can ever attain by partially encrypting data. So with that, why did we actually need to write an Ipcipher specification? Because how hard can it be to encrypt an IP address? It should not be that hard. It turns out it is somewhat difficult. An IPv4 address is 32 bits. All the block ciphers we have to work with operate on at least 128 bits. So we cannot simply use AES in 128 bits mode to encrypt the 32 bits of the IP address 8.4.9.3, because when we put those 32 bits into AES, 128 bits come out. That means that we would have to stuff 128 bits of IPv4 address in our PCAP file, and it would not work. So we cannot simply take a regular block cipher to encrypt an IPv4 address, because it would get us IP addresses that are far, far too long. So what we need is a 32-bit native encryption algorithm. And that one was designed. In 1999, Greg Rose invented skip32, which is a variant of skipjack. And that has been used for a long time in, for example, PostgreSQL to encrypt 32-bit counters, including IP addresses. And it's somewhat of a shame that was created in 1999, because the security level of skip32 is incredibly bad, because it also has a 32-bit key. And a 32-bit key can simply be enumerated on my Raspberry Pi. So that was sort of sad. And that situation lasted until 2015, until Jean-Philippe Amonson released the Ipcrypt algorithm. And this is based on SIPhash, which was invented earlier together with Daniel Bernstein. And this is a 32-bit native block cipher, but using a 128-bit key. And that's exactly what we need. It's very fast. It's so fast that we initially did not believe it. Remember the tool DNS Washer that assigned simple incremental IP addresses, and it turned out that the Ipcrypt variant of DNS Washer is actually faster than the table lookup, which sort of makes sense if you think it through, but it's nice. It's very high performance. It can encrypt a 4 GB PCAP file in 2 seconds. Oh, that's very good for our purposes. The downsides are that Ipcrypt is a relatively unknown algorithm. Not too many people know about it. Hasn't been very well studied. Hasn't been attacked very well. So yeah, we sort of have to take it at face value. And it also has a small weakness that we need to think about. IPv6. This is the one time in our life that IPv6 is simpler. So that's good news. IPv6 addresses are 128 bits long. We have a ton of 128-bit ciphers available. So it's a breeze compared to IPv4. So we can simply use AES 128. And with the one twist that whenever you normally use AES, you use it in a mode like a CBC or counter or some of the more advanced modes. And here we actually just need a raw AES operation, because every time we encrypt an IPv6 address, it's going to encrypt to the same IPv6 address. I spent a few hours finding how to do this, and that's why I left this little bit of code here so that other people do not have to spend this few hours doing it, because you can achieve the same thing in a lot more typing than this, but it will boil down to the same. The key. Encrypting this stuff, like I said, we said, okay, we have a 128 bits key. And the very best way to do this is to take 128 very random bits. That's the best way of doing it. But it's a little bit more work to actually type that in on a command line. And we actually need to do more work, because if we get a human being to type in 16 bytes of random, for one thing, people are not very good at typing in random. And secondly, Ipcrypt, even though it's very fast and stuff, suffers from a related key vulnerability. That means that if you hand type a key and a day later you hand type in a similar key, you will find out that that the output of the encryption algorithm has only changed a little bit. And that's not something we'd like to see in an encryption algorithm. So within Ipcipher, we have said, if you want to encode IP addresses, you have to do a key derivation step in there. That means that you can start using passwords entered by human beings, which are then fed to a key derivation algorithm to get a 128-bit random key. And we asked around a little bit what key derivation algorithm we should use. There are very fancy ones out there that can use gigabytes of memory. That did not seem appropriate for the security level we're aiming for, so we ended up doing PBKDF2, which is RFC 2898. And this allows you to enter a passphrase, which is then turned into 128 bits of key material. So we wrote this up. It's on powerdns.org/Ipcipher. This is freely licensed and open for everyone to use, because the key thing we care about is we have customers and PowerDNS users with a pressing need to encrypt IPv4 and IPv6 addresses, but they also have a pressing need to, in an interoperable way, be able to decrypt those addresses again. So the idea for this is that within your name server software, if it produces any kind of logging data, like for example DNS tab, that you can set an Ipcipher key within your software or an Ipcipher passphrase within your software, and that all your DNS tab logging is only leaves the process in a pre-encrypted fashion. But in order for us to interoperate, we need a standard or a specification. So we wrote this down, and while writing it down, we attracted actual interoperable implementations. So there is now an implementation in Rust, and there are full Ipcipher implementations in Go and C++. And the specification also comes with test vectors, so you can be sure that you're doing it correctly. And it only took like 12 iterations before it turned out that the first interoperable implementation actually interoperated, because writing standards turns out to be hard. But we're there now. Next to the specification, which is really technical, there's also a document that says these are circumstances in which it is advisable to use Ipcipher, and these are circumstances in which it's not advisable, and this is how you should do it. So many of you are seasoned professionals, and you're already thinking about the many ways in which this could go wrong. And there are indeed many ways in which it can go wrong. The most famous case about this, and it's now it's an old story, it turns out, is from 2006, when AOL decided to release 20 million search queries from anonymous users. But crucially, you could still correlate, you could still get a list of, let's say, user 4417749, and you would get all their search queries. And then the New York Times got involved with that, and they quickly found out within a few days that based on people's search traffic, they could actually re-identify these AOL searcher numbers into actual people. And it turned out to be remarkably easy. And so you can pseudonymize whatever you want, but as long as you have enough data to work with, you will be able to re-identify users. And as an example for that, if you find anyone performing the following 5 DNS queries, powerdns.com, which is PowerDNS, of course, Open Exchange, that is our parent company, mail.ubertnet.nl is my own IMAP server. I have a DNA hobby, so I visit the National Institutes of Health website. ds9a.nl is my own website. If you find anyone looking up these 5 domains, you have either found a Google crawler or you have found me. It is child's play to re-identify people if you have enough DNS data. So it's not good enough to say, look, we keep logs of everything and we're not protecting them anymore because they've been pseudonymized. It's not good enough. You need to do more. So here are some specific risks to think about. One of them is a forced known plaintext attack. So for example, someone who wants to attack this, they could, and they know you are logging all your DNS queries. Okay. Then they send you, let's say, 4 billion DNS queries, one from each IPv4 address. And they know you're logging all that. And once you then get access to the log, you find all the known plain text that you attacked in there, and you have a nice dictionary that says, well, 1.2.3.4 apparently ends up as 12.13.14.15. So that is a trivial attack, which of course only works if your attacker already had access to the data beforehand and was able to insert queries into it. A nice one that came up during the specification and standardization discussions was that if you have an IPv4 header, there is an actual super stupid checksum in there. If you only anonymize the IP address and do not change the checksum is a pretty nice hint to the identity of the original address. So if you are replacing IP addresses, then also update any checksums or zero out any checksums, because otherwise you are leaving pretty strong hints. The other thing is, if you keep on using the same encryption key for hours and hours, then you are providing a ton of clues about who owns what IP address. The other one is forgetting to encrypt all IP addresses. So let's say you are reading log files and in text format. There are many ways in which an IP address can appear, like with a port number attached, or an IPv6 address could be between square brackets, or you could even have a scoped IPv6 address. So you need to make sure that you actually replace all of them, even the ones that you may not quite understand. The other thing that is pretty bad, let's say I do a query for whoami.akamai.net, and that will return an IP address in the payload. Yeah, should I encrypt that? Should I not encrypt that? But it's a pretty strong hint. So a second copy of the IP address also frequently hides in ICMP messages and in tunnels. So it's nice if you only replace IP addresses on the outer header of the packet, but the inner packet might then repeat that IP address. And WebRTC is another protocol that is known to leak a copy of your IP address. The other thing that you have to think about is, let's say someone is doing a lookup for a pool.ntp.org, or you are encrypting the IP address of your own name server. The IP address of your own name server is not actually a secret, but by encrypting it, you are providing a piece of known plain text. So it's, for example, the tool DNS washer carefully does not encrypt the IP address of your name server itself, because it assumes that you don't want to keep your own IP address secret from yourself. So the advice here is that if you are doing any kind of anonymization, drop any traffic that you don't understand. So if you have a PCAP full of DNS traffic and you encounter an ICMP packet and you don't know how to deal with that, drop it. So only leave around traffic that you actually understand and know how to anonymize. Frequently use a new key. There is no reason to use the same key for 24 hours. So if you want to hand over data for analysis, use a new key every time. That means that your other department is not able to go back to other log files and correlate people. The third one is, do not enable your second or third party researchers to influence the recorded data. So as I said in the first bullet, if someone adds 4 billion packets to your trace, well, make sure that they don't do that. And finally, ponder retaining unencrypted, well-known IP addresses, like the IP address of your own name server. So with that, we have heard a lot of downsides now, because you cannot simply publish this pseudonymized data. It cannot be done. And also, various privacy regulations do not allow you to say, well, this IP address has been changed, so now it's no longer privacy relevant. The GDPR specifically, by the way, discusses pseudonymization as part of privacy by design. And it's very clear that it says this is something you should be doing as part of privacy by design, but it's not enough. You're not done if you have encrypted IP addresses. But in one sense, it may actually save you one day, because let's say you have a leak of recorded DNS traffic, or of course web server traffic, compare the impact of leaking actual data, actual IP addresses, with the impact of leaking encrypted IP addresses. You look like 10 times better when you say, look, yeah, it's bad, and we didn't want this to happen, but still, it's still encrypted, and the key was not leaked. So the upshot of this really is that the advice with a C is pseudonymize wherever you can, but do not treat that as a license to share the data wider than you did before. So maybe interesting also is the status. Where are we? We now have interoperable implementations, so that is a major step. DNS dist, our own DNS load balancer and mangler and distributor, can apply Ipcipher with logging data, and our own DNS washer tool can now also use Ipcipher to encrypt IP addresses inside PCAP files. So while this is all pretty fresh development, you can actually use this. There's a very good reason why you can use this now. PowerDNS is deployed in legal environments where this is simply mandatory. So we did not entirely build this out of goodwill. We simply had to build this because otherwise our customers would go out of business, because they have to square the responsibility of doing security analysis with harsh privacy regulations, and this was the way they were able to do both of these. So it's for real. With that, a few notes, future work and acknowledgements. While Ipcrypt looks sound and it's very simple, there are no papers written about it. There are papers written about SIP-hash, which is the parent algorithm of Ipcrypt, but not a lot of people have actually looked at the Ipcrypt algorithm. So more, cryptologist attention would be more than welcome, and people trying to hack it. Lots of people came up and they said, well, can we group a whole /24 or /64 IP addresses together and encrypt that to one encrypted IP address, so we can still group packets, because we can no longer group the packets after encryption. And there are some obvious ways of doing this, but there are also some obvious ways of doing it wrong. Other people have said, look, we would like to maintain the class of an IP address. So let's say something was an RFC 1918 private space IP address. We would like for it to stay a private space IP address after it was encrypted. Or if something was a multicast or a broadcast address, we would still like to be able to see that. This does not appear to be simple to do, but it is a reasonable thing to want. What people immediately came up with, they said, well, that's nice that you can do this for IP addresses, but we also want this for credit card numbers and bank account numbers. So that's also nice. Even though we now have interoperable tools, we do not yet have a tool through which you can pipe a log file and that it will automatically do this for you. And of course, this is a simple exercise left for the reader, or a small matter of typing, but the small matter of typing still has to be done. Another obvious thing is, of course, that this screams to be turned into an internet draft or whatever, and we haven't done that so far. The simple reason we haven't done that so far is that we have a screaming need to deploy this right now. It has to happen right now, and we didn't yet have the time to wait for the 6 months or 1 year that it takes for a draft to get published. So there is quite some stuff that still needs to be done. Input is more than welcome. And with that, I'd also like to thank, of course, Jean-Philippe Amonson, who not only provided the Ipcrypt algorithm, but also explained how to do this well. Paul Hofman provided feedback. Silke Hofstra, the first interoperable implementation. Frank Denis supplied a C version of the algorithm. And Edwin van Vliet and Job Snijders provided various kinds of feedback. And that ends my presentation. If you want to know more, this whole presentation can be found on tinyurl.com/ipcipher. It will also be published on the webpage of this workshop. And through that link, you can find links to the actual specification and the various implementations that have been created so far. And with that, I thank you for your your attention.
So we'll have like 5 minutes for questions since we started a bit late, we're running late. So say your name when you come up to the mic.
Hi, this is Daniel Gilmore.
Oh, you got to switch it on. Okay.
This is Daniel Gilmore. Thank you for this work. I'm happy to see this happening. I have 2 questions for you about it. One of them is the keyword that I'm sort of missing from this presentation is format preserving encryption. That's the term that it seems to be known by this approach is known by in the industry and in the and so I'm wondering whether you've compared Ipcipher with FF1 or FF3, which are format preserving encryption techniques that are standardized by NIST already. I'd be curious to hear about that relationship. And then secondly, I'm wondering whether you have any thoughts about the key rotation that you mentioned. I think that's great guidance. And I think what we actually need is tools to automate that guidance. So you can set a policy to say, here's the keys that we're going to encrypt to as we change over, and we'll rotate them over time. I mean, I'm wondering if you know of any tools that are doing that sort of automated key rotation to simplify policy setting.
I see that. So the mic is very low.
I'll try that one.
Try this one. Okay.
Yeah, but I think I did get it.
Okay, maybe you can repeat it quickly.
Yeah, so the first question was that and thank you that there is industry prior work called form preserving encryption. That's great. And I have to admit, I did search far and wide if there was anything done like this, because otherwise I would not have done it. And apparently my searching has not been good enough. So I'll be taking a very good look into if any of that is applicable and if we maybe can just refer to it. So thank you for that. And the second part is, am I aware of any key rotation policies and other stuff? I think this is indeed very good, but because it's all well and good to tell people, look, you need to rotate your keys a lot and then not give them the tools to do it. Or even worse, tell them, look, you need to restart the whole server if you want to change the key. So I think that definitely needs to happen, because if we don't provide that kind of tooling, then it's not going to happen, and we will have this welcome 123 key that will be used, or even worse, welcome 2018, and that will be using that key into 2022. So yeah, that's a very good suggestion. Thank you for that. But I'm not aware of anything existing right now.
Good talk. Thank you very much.
Can you shout into the mic?
Yeah, this is Wes Harder, USC ISI. We have a tool called Encrypted ISI that does anonymization across a definable bit boundary. So you can say anonymize everything in /24 or /16 or whatever, that we use to anonymize e-root data when we submit it to DNS OR. And that whole concept of how to anonymize DNS OR data is being done in our RSAC caucus right now. So I highly encourage you to contribute to that work effort. They're sort of midstream right now, but anybody is allowed to join the caucus and participate. Anybody is allowed to join the caucus if they apply for membership in the process. Yes. Sorry, Paul's correcting me, but you can apply to the RSAC caucus. Anyway, that work effort would be love your set of eyes.
Okay, I'm very sorry to say that I caught almost nothing of that, except that I hear that you have some tooling already and we should probably look into that.
Eric, can you hear me? It's off. I'll take that as a no. The audio is really not here.
Yeah, it's funny that it's not getting to the remote side.
So, Eric, this is Paul Hoffman, if you can hear me.
No. Do you want to come up? Barrett, you can hear me, right?
Yeah, I can hear you very well.
All right, so people come
We
up
tested
here.
this earlier.
Yeah. Okay, so come up here. There's something about shouting right here at the podium that helps.
Okay. So, Barrett, briefly, because we only have a few minutes, Wes was talking about the fact that RSAC caucus, which I had told you on the mailing list, working on it, so, but also that USC ISI has a tool that does do preservation by bit boundary that they have published, and that's one of the considerations in the RSAC caucus work as well. The problem with that, one of the things you were talking about with IP crypt, underneath Ipcipher is how fast it is. Theirs is very slow because it actually has to do a whole lot, but that's one of the considerations that we're having. The other thing I wanted to bring up is you kept talking about being able to reverse, and that's why you're using ipcrypt. Some people who are doing this actually don't care about being able to reverse it. They just want to anonymize, and therefore they can do mixing that is actually not encrypted. So you can hash and truncate, for example. So we talked about that as well. So let's talk more about that. And yeah.
Okay. All right. Why don't we
Thank you very much.
thank our speaker? That was a great talk. Great start.
Thank you for having me.
And now I'm going to try to bring Philip. Oh, did anyone type any questions? No, I don't see any questions on the. Okay, so now let's try to bring Philip up here for the next talk by Philip Winter. Okay, here are his slides, and hopefully we also will have his vision. Okay, and you want to do presentation mode. Okay.
Okay. I hope you can all hear me and you can see my slides. Okay, first I have to apologize for not being there in person. Unfortunately, my flight got cancelled last minute yesterday, so I have to do it remotely. So my name is Philip, and I'm going to tell you a little bit about onion domains because I think they have a bunch of really interesting privacy and security properties.
Oh, let me just do a sound check here. Can people hear Philip well?
Can you hear us, Philip?
I can hear.
Yeah.
Perfect.
Yeah. You might want to move your mic a little closer to your mouth. He's
okay. I will try.
Remote speaker. And also introduce yourself, okay?
Mm-hmm.
Sorry,
okay.
So good.
No problem. I hope it's better now. So my name is Philip, and I will tell you a little bit about onion domains because they have a bunch of very interesting privacy and security properties that come at the cost of some usability issues. But I think there are some lessons to be learned on DNS. And so onion domains are part of the Tor network. So the Tor project is developing the Tor browser, which you can use to browse the internet anonymously. And an aspect of this is onion services. So these are basically TCP services that run only inside the Tor network and that are, as a result, anonymous. And the way these onion services work is quite different from normal domains. And this is an example. This is the onion domain of the Tor project's website. And it's different from normal domains in a bunch of ways. First, you will notice that it ends in a .onion. And this is a special use domain that is now reserved only for the Tor project. So DNS itself doesn't understand it. Still, if you look at a root DNS server, you will still see a bunch of .onion requests going there because of mistakes, because of misconfiguration, and presumably because of DNS prefetching. But it's not understood by DNS itself. It's only routable inside the Tor network. And the next part is the most idiosyncratic part of onion services. It's basically a bunch of seemingly random characters. And what you see here is basically the hash, the base 32 encoded hash over a public key. And this makes the final domain. And as a result, it's really difficult to remember because it's basically random characters. I will show you later that there is a way to make them a little bit more memorable, not 100%. It's definitely not at a point where it's as easy to remember as normal domains in DNS, but it could be more tolerable. And the way they're resolved inside the Tor network is over a distributed hash table. So there is no single entity that controls the entire process. There are currently a bunch of weaknesses that are being worked on and that are being fixed in the next generation of onion services, but at least there is no single entity that controls the entire process. And finally, for the sake of this example, this is an HTTP URL. But you're not limited to HTTP or HTTPS. I briefly mentioned that onion services are based on TCP. So whatever service you're exposing over TCP, you can use an onion service for. Typically, it's used for the web, but you can also use SSH over it or chat protocols. And SSH is an example that's really popular because you can expose an SSH service over an onion service behind a NATS device. And this is a brief overview of the technology. When it comes to the user interface, it's designed to be seamless. What you can see here is the UI of Tor browser. And at the top, you see the normal website, torproject.org. And at the bottom, you see the corresponding Onion service. A tiny quirk you might notice is that the Onion service does not have a security indicator at the moment. So for the HTTPS website, you see the green lock, but this is lacking at the Onion service, which is a bit of a problem because it greatly undersells the security and privacy that an Onion service can provide you. But this is something that the Tor project is currently working on, but we're not completely sure how the indicator is supposed to look like because it's not quite the same as HTTPS. It does provide a little bit more than just that, so we're experimenting with different ways to express the security. I want to give you a brief overview of the great security properties that Onion services provide you with. So first of all, the domains are self-authenticating. Assume you have a person that gives another person an Onion domain. And once she takes the Onion domain and establishes a connection to the Onion service, you get the public key over it. But the typical question you have in security protocols is now, can you trust the public key, or what sort of guarantees do you have that it is the legitimate public key? And since these domains are self-authenticating, all Alice has to do in this case is hash the public key and compare it to the Onion domain she received earlier. And if it matches, then you know that you're connecting to the right Onion service. And this is a really strong security guarantee, but as you can see, it comes at a usability cost because these domains are just way harder to remember than normal domains. The next part is Onion services are end-to-end encrypted. Once you've established a connection, you basically have end-to-end encryption between Alice and the Onion service. However, you may still want to run HTTPS on top of it because an extended validation certificate gives you some sort of assurance of who is the entity that applied for the certificate. So it's basically guarantees orthogonal to security, but there are reasons for this to make sense. And this is what Facebook, for example, is doing. Despite the end-to-end encrypted connection, they're having an EV certificate on top of that. Also, both client and server are anonymous. The client doesn't know the IP address of the Onion service, and the Onion service doesn't know the IP address of the client. It looks like this. They're basically both having a circuit, a core connection to a middle point in the network. And for the sake of simplicity, I'm only plotting 3 hops here inside the Tor network. In practice, it's actually more than that, but I will try to keep it simple for this argument. And the middle point in the Tor network also has no idea what it is relaying. It doesn't know the origin, and it doesn't know the destination of the connection. So it's possible to have a 2-way anonymous connection here. Despite all of these great properties, traffic analysis is still possible, meaning that if you have an adversary, such as an ISP, that is able to sniff your network traffic, this person can look at things like packet lengths, packet timings, and the directions packets are traveling in to infer some of what is going on in the underlying Tor connection. Of course, there's a lot of inaccuracy in it and presumably false positives, but it is something that we're struggling with at least a little bit. Probably the biggest issue that you may be encountering is good old configuration error. The people often don't set up their Onion services correctly, meaning that one classical example is that the Onion service listens to both the Tor daemon and the broader internet, meaning that internet-wide scanners could just look for web servers that serve the same page as an Onion service does, and then conclude that the web server they just discovered on the internet is the Onion service. So this is one of the configuration mistakes that people frequently make. So this is probably even the biggest issue that people are struggling with when it comes to Onion domains. All of this is great, but we're having a lot of usability issues with. We have the very long domains that are problematic. Onion services are also private by default. So if you set one up, it doesn't just automatically show up on the internet. You need to take disseminations into your own hands. It's also a little bit tricky if you run a website to announce that you have a corresponding Onion site, because there is no standard way to do that. It's up to you to take care of that. The number of hops between a client and the server causes a lot of latency, which is a little bit annoying to deal with. And if you look at a domain like this one, you don't know what is behind it. So it can often be a bit of a surprise and not always a pleasant one to discover what is behind an Onion domain. And this is where our work started. So about a year ago, we set out to do a usability study, which consisted of interviewing 17 people and of launching an online survey that ended up attracting around 800, 900 responses. We're still in the process of writing up our results. We have some preliminary results available online, and I'm going to give you a brief overview of our most interesting findings so far. First of all, we asked people how hard they think it is to remember given Onion domains. So what you see here is 4 different domains. The one at the top is the one that is run by the Tor project. The one at the bottom is the one run by Facebook, which is slightly easier to remember. And the 2 in the middle we made up. And as you can see, the prefix in the domain becomes easier and easier to remember. And it comes as no surprise that users perceive these domains to be easier and easier to remember. The first one, the vast majority considers at least somewhat difficult to remember. And the bottom one, Facebook's, is considered by almost all at least somewhat easy to remember. And again, this comes as no surprise, but Facebook's domain was very, very difficult to generate, while the one at the very top was generated almost immediately. So it's not very easy to get these domains to be at the bottom here with Facebook. And since it's so difficult to remember these domains, you probably want to deal with them some other way. And we asked people how they handle a large number of Onion domains, and this is the result. You can see that a very popular strategy is to just bookmark them. Use the bookmarking tool in Tor browser. The problem with bookmarks is that it basically leaves a browsing trail on your computer. So as a result, people fell back to saving domains in local text files and also encrypting them. So if someone seizes your computer, for example, they cannot immediately see what Onion domains you're interested in. And what is really striking here that a quarter of our respondents said that there is just no good solution. They're not happy with the way it works now. And I think this is a really good opportunity to come up with tools and perhaps Tor browser extensions to make this a little bit easier for people to deal with. Other than that, a couple of people tried to memorize domains. That may work well for 2 or 3 domains, but certainly not for dozens, the way we do it for normal domains. And another reason is another thing people do is to just refer to trusted sources, to trusted websites or aggregators or people. And apparently some even use pen and paper to write them down physically, which may ironically be more secure than just use the bookmarking tool in Tor browser. I mentioned earlier that there is no automatic way to publish Onion domain. And we call this the Onion domain discovery problem. So once you set up an Onion service, it's up to you to disseminate it. You may want to publish it on social media or find another way to get people to use your Onion service. And what seems very popular is 3 things. People go to social networking sites. So there are a bunch of popular subreddits where people discuss, for example, darknet markets or domain topic-specific Onion services. There are also aggregators. I will show you a screenshot of one later, where basically people set up services to aggregate as many Onion domains as possible and categorize them and curate those lists to make it easy to discover new domains. Random encounters are also very popular. You just browse the normal web and occasionally you stumble upon an Onion domain and there you go, you just learn about a new one. And those are basically the 3 most popular ways to stumble upon new Onion domains. And this is what looks like in practice. What you see here is the website of ProPublica. And at the bottom in the footer, it's not very easy to see. You see a link to the corresponding onion service at the bottom right. And ProPublica is running the very same website over an onion service. So you can just go to the onion service and browse their website with a bunch of additional security and privacy properties. While we were running our survey, we got a bunch of really interesting responses that I want to share with you. And one thing that surprised me a little bit is that in our survey, we brought up things such as onion-site search engines and aggregators, and a bunch of our respondents weren't even aware that these existed, while we assumed that it was well known to everyone. And I'm basically cherry-picking the quotes here, so this is not necessarily a theme that was common in a lot of responses, but I just found it surprising that these tools that make it so much easier to deal with onion services are not even known by some people. This person, for example, said, I wasn't aware that onion-site search engines exist. It's been near impossible for me to find them so far. And this is what such an aggregator looks like. This is a list of onion services, a curated one. So you see each row here represents an onion service. There is a column for the title to make it a little bit easier to understand what is hosted on the onion service, because as you may suspect, there is a lot of illegal content there involving drug trading and also child pornography. So a lot of people in our survey results also said that they're very careful about what domains they visit because they just don't want to have any nasty surprises. This is why it's really important to have some sort of label or title associated with it, so you know what you're getting into. And there is also a lot of churn in onion services. They come and go, sometimes very quickly, so it's important for these aggregators to be curated and to dump old onion services that are no longer around. And I briefly mentioned earlier Facebook's really pretty looking onion service, and we call these vanity onion domains. The idea is that you have a domain, and by default, they're really ugly and not easy to remember. But you can generate the underlying key pair over and over and over again up until a point where you suddenly end up with a good-looking vanity domain. And that takes an awful lot of work, and it's exponential work. So the more pretty-looking characters you desire, the more work you have to throw in there. And I have 3 examples on the right. The one from ProPublica, the New York Times recently set one up. I think the best one, or the easiest to remember one, is still Facebook's. This was so surprising to people that there was a large outcry when this was published, because people thought that someone discovered a vulnerability in onion domains, because there is absolutely no way anyone is able to come up with a domain like that. But it turns out if you have an awful lot of computing power and an awful lot of luck, it is possible, but it's definitely an anomaly. And we weren't sure if the advantages of onion domains outweigh the disadvantages. And after looking at the data, we're still not entirely sure. So the good part is that by looking at these domains, you get a sense of what is behind it. If you see New York Times, blah, 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 you probably assume that it's the New York Times behind it. So this is definitely a good thing, that it reveals a little bit of what the content of the onion service is. Probably the most significant bad aspect is that they breed a false sense of security, because it conditions people to only verify the easy to remember part and ignore what comes after it. So if I were an attacker, I could just take, I could target the New York Times onion service and generate the same prefix and hope that people only trust the first couple characters and ignore what comes after it. So that is a huge issue, and it's also economically unfair. A lot of people in our results said that by having vanity onion domains, you're basically making it possible to wealthy and powerful organizations such as Facebook to generate really pretty looking domains, and normal people are completely unable to do that because they lack the computing power. And it's a little bit difficult to compare these good and bad aspects, because we're comparing apples to oranges. But then again, there is not necessarily a great way to prevent vanity onion domains. I suppose we could incorporate a proof of work, but then again, it would just make it a little bit harder to generate them and not make it possible. So maybe it's something we just have to deal with and educate users about the disadvantages. But here are a couple of quotes that hopefully emphasize what I just said. So one survey respondent said, I only memorized the first part of the domain, which again may lead to security issues if you blindly trust the prefix. We also found it surprising that there are a lot of technical misunderstandings around onion services. This person wrote, I understand vanity onion domains are a sign of the weakness of the hash algorithm used by Tor. This is not really true. I guess it depends on how you define weakness, but the hash algorithm itself, which is SHA-1, is still mostly safe, at least for the purposes it's being used here. But again, people seem to misunderstand onion services a lot. For example, some believe that the random characters are the reason why onion services are hidden. And they believe that Facebook, for example, is no longer hidden or anonymous because it doesn't have random characters in it. Here is another example. These people who created their onion name using Scallion or other tools should notice that other people can make the same private key. So Scallion is a tool that automates the creation of vanity onion domains. And again, this is not true. Simply by using a tool such as Scallion to generate a vanity onion domain, it doesn't mean that I'm able to create the same private key as another person. So this is just wrong. But for some reason, there are a bunch of bad mental models out there regarding onion services. So we believe that there are a couple of ways that we can push things forward. So we have a bunch of really great security properties and a bunch of significant usability issues. And how do we get rid of these usability issues? First, we believe that if we can enhance Tor browser by storing bookmarks encryptedly, I think we would help a lot of users, because that way, if, like I said, your laptop gets seized, it doesn't immediately reveal the onion domains you're interested in. I think there is also merit in coming up with a mechanism that takes care of announcing onion services. So we probably want to have some kind of opt-in publishing mechanism where you could express in your configuration file that my onion service isn't entirely private. I actually want it to be well known, and then have it published to some kind of public log file that people can use and perhaps make it pretty by building some kind of web front end over it. We probably also want some kind of, not really a redirection mechanism, but take the example of ProPublica. If they have a website, they might want to have some kind of mechanism to express to your Tor browser that there is an alternative service available. And maybe we could have some kind of pop-up or some kind of toolbar at the top that informs you that there is an alternative service and asks you if you want to use it maybe for this session or for all sessions, something like that. And again, the Tor project is currently working on that. Some UI elements are misunderstood, so I suppose education could go a long way towards reducing these issues. And yeah, people also complain in general that documentation efforts are lacking, and localization efforts too, because while Tor browser is available in a lot of different languages, the documentation unfortunately isn't. It's only available in English. Finally, I only told you about the current generation of onion services, but the next generation that is already finalized and currently being tested and in the process of being rolled out is using way, way longer onion domains. So if you think that you may be able to remember some of the current generation domains, forget about the next generation domains. And you can see an example at the bottom. And we thought that this may be one of the major hurdles regarding the adoption of the next generation. It turns out that it may not be as bad as we thought it was, because people increasingly treated onion domains as opaque identifiers. It's no longer something that you look at and you memorize like ordinary domain names, but it's just a blurb that you bookmark or that you write down and you don't really think about it, which I think raises some interesting questions about the value of domains in general. For example, if we have useful browser tools, do we need domains to be eventually readable, or can we just tell users that it's just an opaque identifier that you don't need to worry about? And the reason they're so long is because the new generation switched to elliptic cryptography, and the entire public key, instead of just a hash over it, is now embedded in the domain name. So again, it's going to be interesting to see how this will turn out, but it may not be as big of an issue as other aspects of onion services. And this brings me to the end of it. We have some preliminary results available online. You have my email address here. And I want to finally thank the Tor project for helping us out a lot, the broader Tor community for taking our survey and agreeing to be interviewed, and my collaborators that you can see here, Annie, Laura, Marshini, and Nick. Thanks a lot for your attention.
Okay, great. Thank you so much, Philip. I want to propose, in the interest of time, that since you were going to talk originally in the panel session at 2 o'clock, that you be around for that session and people ask questions about your talk during that time, so we can bring up Basilio to give his talk. And let's see if we can find your talk on here. You want to do that for me, Karen? Or, okay. Okay. Yeah, so let me find, let's unshare this one. Can you stop sharing? Thank you. And now let's see. Let me go out of full screen. Sorry, this takes a moment to do this transition. And now I'm going to share a screen, but I have to find one. And which one is yours? This one. Yes. Okay, and share screen. Okay, didn't do the right thing though. Stop this share. Try that again. Share screen. And back to yours again here. Share screen. We're still getting Philip's. Philip, have you stopped sharing?
I stopped sharing.
Okay, why am I still getting yours when I think maybe you want to come figure this out. We haven't. I'm seeing the window for it, but when I pick that window, I'm not actually getting it. Yeah. See, we're getting Philip's.
I think this is a different window.
Oh, we're just in the way, maybe.
Oh,
yeah,
these
they're
are
all
like,
here. Okay.
Okay.
Got it. Right. That's not it either. Okay. I'll have to find all those again, but that's okay. I'm actually, oh, it's all the same window of, it's all the same thing here, right? Oh, it's all the same app. It's all the same app, yeah, that's the problem. So you're like the very last one, unfortunately. You're all getting a preview of the first screens of everything. Okay, there you are.
Okay.
All right. Zed, introduce yourself, and we're glad you're here. Thank you. Okay, and then folks, we'll run about 10 minutes into the coffee break, so you'll have to rush and get your coffee and network at 1.5 speed instead of 1x, okay?
All right, hi everyone. My name is Basilio Imana, and I'm a first-year PhD student at University of Southern California. And today I'm going to talk to you about our work on enumerating privacy leaks in DNS data collected above the recursive. This is a joint work done in collaboration with my advisors, Alexandra Korlova from University of Southern California and Join Heidemann from USC Information Science Institute. The DNS system is the starting point for most activities on the internet. And DNS queries that originate from our devices can say a lot about what we do online, and thus may have privacy implications. And the fields in a DNS query that are relevant for privacy issues are query names and the associated type of the query, and the source IP, which is the origin of the query. And these fields may have different interpretation depending on where in the DNS hierarchy the data is collected from. For example, when a query goes from a stub resolver to a recursive resolver, the source IP identifies the stub, but when the recursive resolver submits the query to the authoritative service on behalf of the stub, it replaces the IP address is replaced by the IP address of the recursive resolver. And because of the recursive resolver acting as an aggregation layer, the data collected at different points in this hierarchy may have different privacy implications. So why do we study DNS privacy? The primary motivation behind our work is that researchers and DNS operators use DNS data for purposes such as improving the DNS system and also sharing it with other researchers. A good example is the DNS.org Ditto initiative that makes authoritative and recursive DNS data available for research purposes. But the problem is that the privacy risks of analyzing and sharing this data is not fully understood. And also from the perspective of users, yeah, DNS privacy might be an unfamiliar topic for most end users, but some users still may care about their privacy because DNS queries represent end user actions. So in light of this need, our main contribution in this work is to enumerate different classes of leaks in DNS data that's collected above the recursive. And out of those we enumerate, we take 2 of those classes and we look at how often they appear in root DNS traffic. So a quick overview of previous work. A lot of work has been done into both understanding the risks and proposing mitigation mechanisms such as DNS over TLS and query minimization. But the main point I want to make is that most of prior work in terms of deployment has focused on DNS data below the recursive. And by below the recursive, I'm referring to traffic that goes from a stub to a recursive. And we use the term above the recursive to refer to traffic that goes from recursive resolver to authoritative server. So the data below the recursive has more privacy implications because it's closer to the end users, and the recursive resolver sees the traffic from each DNS client. And consequently, more effort has been put into securing this link between the stub and the recursive. And one such example is Stubby, which is a private DNS client that uses encryption to achieve that. Now, intuitively speaking, the data above the recursive may seem to pose minimal privacy risks because the recursive resolvers are often shared by many users. So it aggregates and mixes traffic from many users and potentially hide their identity. So in this work, what we do is we re-examine this assumption and look at what kind of queries might leak information above the recursive, and some of which may happen even when there is aggregation at the recursive. So in enumerating the leaks, we consider 2 types of adversaries. The first one is a passive adversary that may have access to the traffic between the recursive and the authoritative server, and also may have server logs of the data at rest in a compromised server. And we also consider an active adversary that may make a user to inject queries and observe those queries at an authoritative server that's under the attacker's control. This is similar to the force attack that was mentioned in the talk earlier on IP encryption. So in reality, these adversaries might be ISPs or DNS service providers, and also operators, researchers, or individuals that may have access to a compromised server. And an adversary might be interested in a specific individual behind the resolver, or also be interested in the group as a whole that's sharing the resolver. This might be either a household or an organization where all the users share a single recursive resolver. And in our analysis, we also assume the adversary may supplement the network traffic with external information about either domain names or IP addresses that are associated with the targeted group or individuals. So in our work, we enumerate 4 different types of leaks, 3 of which fit into our passive model and 1 into the active model. So I'm going to go through each of them one by one, starting with the passive. So the first one is what we call trackable names, which are unique identifiers that may be associated with a specific individual or group. For example, a user might use their own last name for a domain name of a server that they use to host their email or calendar services. For example, ClintonEmail.com was the private email server that Hillary Clinton used. So if users use such kind of names to host servers that they use for their daily personal activities, appearance of queries to such names in the data set might indicate some information about when they do what during their daily routine. And this can be also powerful because the leak is in the query name itself and has nothing to do with the source IP. But on the other hand, this attack might be difficult because such association between an individual and the domain name that they own requires some external knowledge. So it would be easy to look for if you know what if the adversary knows what to look for, but otherwise it would be difficult. The second class of potential leaks we looked at are IP addresses and key names. Just for clarification, this is not the source IP of the query, but IP addresses that are embedded into the domain names of the query. So we looked at different common categories of queries that have IP addresses and key names, and we looked at the privacy implications of each category. So the first one is a reverse DNS query, which is mostly used for purposes such as troubleshooting a network or logging website visitors. And because it has a variety of common use cases, we don't consider this to pose minimum privacy risks because it leaks very little information about what's going on. And the second type of query is DNS-based blacklist queries, which are IP reputation systems that are used for filtering spams. And also, this don't identify individuals, but frequent appearance of a specific IP in such kind of queries can indicate that a person might be trying to spam other users. And the third category is customer-provided equipment, queries related to customer-provided equipment, which can be those provided by either ISPs or other cloud service providers. And these queries often contain a keyword such as static or dynamic that can be used to differentiate between static and dynamically assigned IP addresses. So for example, if the query contains static, it might indicate a longer association between the customer and the equipment. So overall, the privacy implications of IP addresses and query names depend on how often the addresses change, and this can vary geographically, and also it depends on the availability of ISP data that can map IPs to specific individuals, which is not public information. And the third class of leaks we looked at are sensitive domain names. We use this to refer to domain names that are related with a specific health or religion or gender or some other personal information that can be used to profile users. And here are some examples on the slide. So queries to such kind of domain names can be used to infer some information about the users that are making such queries. And here, this kind of queries mainly happen when there is insufficient aggregation at the recursive, because if there are 1,000 or a lot of users sharing a recursive resolver, it would be difficult to trace the query to a specific individual. But when there is insufficient aggregation, it might pose a bigger risk to the individual. And this insufficient aggregation can happen either when there are few users sharing a resolver, or when a person chooses to run a recursive resolver on their client machine. So for active adversary, we considered query injection, and by this we mean an adversary that can cause a user to perform a query, for example, by either sending them an email with a URL or causing them to run a software. And the goal here is to observe those queries at a server that's under the attacker's control. And in order to make sure the queries get to the server, the attacker can carefully choose the domain name, for example, by using a non-existent domain to make sure it pierces through the cache. Actually, a similar technique is used by a diagnostic tool called Nettalyzer, which was built by a team at Berkeley. And what they do is that they append a nonce, which is as a prefix to the domain name, to make sure that each time the DNS queries are made, it persists through the local cache and gets to their analysis servers. So a similar technique can be used by an attacker to observe queries that originate from a user's machine and use that to learn about either which resolver the person is using or what activity is happening on the user's machine. So in the next part, I'll talk about our analysis of root DNS data. So for our experiments, we used Beaveroot's Ditto data from 2017. Because it has a lot of queries, we sampled it with about 100,000 queries from approximately every hour. And we used this data to look at how often two types of the queries we enumerated appear in the data. So we specifically look at IP addresses and query names and sensitive domain names. So for IP addresses, we used regular expressions and keywords that are specific to each category that I mentioned earlier to identify queries that contain IP addresses. And what we found is that about 3.9% and 0.08% contain IP addresses. That's for IPv4 and IPv6. And so this is for the sample. So based on this, assuming that our sample is a good representative, this would mean about 57 million queries per day might contain such IPs in the domain names. And we also looked at how that divides up into the different categories that we looked at. And what we found is that the less privacy sensitive reverse DNS queries contribute to the largest percentage. Here, the y-axis is the percentage of the 3.9% of queries that contain IPv4. So reverse DNS contributes to the largest percentage, but the DNSBL and customer-provided equipment queries contribute to a very small percentage. And in our second experiment, to categorize sensitive domains, we used categories provided by Alexa Top Domains. So we picked 5 categories, and we took all the publicly available domain names for each category. And also the categories also have a number of subcategories. So we make a list and we use that to compare the query names in our DNS dataset to check if they're sensitive or not. And these are the 5 categories that we picked. So the result we found is that in our sample, only up to 1.2% of queries contain sensitive domain names. And this table shows how that's distributed among the 5 categories we looked at. 1.2% is definitely a small percentage compared to the whole traffic. But we do not think this is insignificant because previous work has shown that the DNS traffic has a very long tail with most popular queries contributing to a very large percentage of the traffic. So it is expected that websites that are accessed by a specific class of users would contribute to a smaller percentage. So earlier I had mentioned that specific leaks through sensitive domain names happen when there is insufficient aggregation at the recursive. So we also started looking at this problem of aggregation, which has to do with how many users share a resolver. And in an effort towards that, we looked at how many queries are submitted from each recursive resolver in our data set. And here is a log plot of the number of resolvers versus the number of queries from each resolver. And as you can see, it has a long tail with a few resolvers making a lot of the queries and a lot of resolvers making very few queries. And but estimating the number of users can be challenging because this number of queries is affected by many other factors, such as caching at different levels in the hierarchy and the diversity of DNS clients and also NAT addressing. So in future work, we plan to look further into this aggregation problem and look at how much aggregation there is in the wild. And also, we plan to look at other types of leaks, such as leaks at organization level, For example, isolating and looking at DNS queries that originate from a specific organization's network and trying to use that to infer what's going on in their network. So in conclusion, in our work, we enumerated privacy leaks and DNS data collected above the recursive. And we also used root DNS data to show how often some of this leaks happen in real world traffic. So this is an ongoing work, and there are still a lot more questions to be answered. So if you'd like to follow up or have any questions, this is my contact information. With that, I would like to conclude my presentation and take any questions.
And I think we can take a few questions now because we said we'd go to coffee break in 5 to 10 minutes. So go ahead, Paul. Maybe you want to go up to the front. Oh, here we go.
So thank you. I'm glad that this particular slide is great because people do often forget that when we're talking privacy that there's two very different sides. Two things to note. One is your dotted line goes right through the recursive resolver. That can expose things as well. That is, whoever you're using as your recursive is able to collect traffic and such like that.
Yeah.
I understand you're just looking at what can an outside attacker look at.
Yeah.
My second note is that when you were talking about in the last slide about aggregating,
yeah,
and you were doing that aggregation analysis just by looking at the root server traffic. Right?
Yeah.
That's assuming that that the root servers are seeing representative traffic.
Yeah.
You know that's not the case.
Yeah.
For very large recursive resolvers, they're doing, for example, aggressive NSEC caching.
Yeah.
Things like that.
Yeah.
So it would be. I look forward to seeing how your later research on that because it has a whole lot of holes that affect everybody here.
Yeah.
And one can say, oh, let's better privacy by using a resolver that never sends anything to it.
Yeah.
But then again, that's aggregating to a smaller number. So I'm looking forward to whatever you come up on that. But we've already hit that where, for example, you were looking at the DIL 2017 data,
yeah,
which is interesting because you have all your own data. You looked at the stuff that's sort of semi-public.
Yeah.
But even on that, we can tell that there are major resolvers that just no one ever sees. That you can look for stuff that they would look for. You don't see it across any of the letters. So.
Yeah. All right. Yeah. Thank you for your comments.
I'm actually not short, but Melinda Shore. This is really interesting too. I'm going to be talking about this more this afternoon. But one of the things that we're finding with certificate transparency and logging at 509 certificates is that it's turning into a way for outsiders to aggregate a lot of information about domain names that are being certificates are being issued or that are being registered, and that's being used by attackers in some novel ways. For example, I don't know if you're familiar with bucket stream, but basically what they explain is there's switching the CT logs for the issuance of S3 buckets, S3 buckets, and then they're using that to probe S3 buckets for access permissions. So we're seeing a lot of that kind of thing, and DNS privacy has really been focused on user privacy, but it turns out that there are these issues with the servers, even though we consider domain names to be basically public information.
Yeah.
But it turns out that when they're easy to access, there are problems that involve. And so it seems like that problem is tied to the problems that we're looking at as well.
Yeah. Thank you for your comments.
Sure. Hi, Eric Zigas, Farsight Security. We specialize a lot in passive DNS and the collection of it, and we've seen inside the passive DNS that there are other things such as people's antivirus, hashes and such, and there's a lot of data in there, and I'd actually be interested in seeing you pursue this more with actual above recursive data, not just at the root, because the root only gets the first query if it's not in the cache.
Yeah.
It'd be nice to actually get a complete set of here are all the queries that came from a name server I believe you'll find some in Diddle 2016 that was submitted from us, and if you need some more, we'd be interested in having you do further work.
All right, thank you. Any other questions? All right, thank you.
Thank you. So it turns out Philip will not be able to be here. He's actually still trying to fly here for NDSS. So if anyone wants to ask him a couple of quick questions before we send you off to coffee break, this is a good time to do it. Hopefully, Philip, you're on the line, are you? Bring back Zoom.
No, I think he's had to drop off, Alison.
Oh dear, okay, all right. Okay, everybody send mail to Philip. Sorry for my confusion on that. And please go enjoy a coffee break. Come back here sharply at the half hour and we'll start up again. We have a pretty packed next session as well. So we will start without you if you're not here. And thanks again, Basilio, for launching the in-room part of our conference. And hopefully everybody's going to network about this because this is such exciting stuff. So, okay.